Welcome back. So, in the last class we discussed how to solve first order differential equations using the Euler, improved Euler, modified Euler and the Runge-Kutta method, and we saw that the Runge-Kutta method was better and more accurate by quite some bit. So, basically what we are going to do is focus on discussing second order differential equation today, and in particular we shall take the example of simple harmonic oscillator. As I will show you in just one or two steps, that second order differential equation solving it is pretty simple once you know how to solve the first order differential equation. Basically, the second order differential equation we will be writing it as two first order differential equations and solving them in parallel. Okay. So, let us focus and get into the details. So, suppose that you are asked to solve m d2x dt2 equal to minus kx, which is the equation of motion of a simple harmonic oscillator, a spring if you like, and of course, this can be solved analytically, but the reason we shall take this example to learn the system and then of course, go over to more complex systems is because again that this is analytically tractable. Whatever your solution is, you can compare with the exact results and see whether you are getting correct results. Once you have developed the method, you can of course substitute this minus kx by more complex potentials, right. Now, m d2x dt2, there is a second there is a double derivative of x with respect to t, that is why it is a second order differential equation, and m is mass and that is equal to minus kx, k being the spring constant, right. And this equation can be written, this m you can write it like this, and then you basically this k by m is a constant and that decides the time period of oscillation, right, and this is your second order differential equation. Now, this can also be written as dx d2x dt2, but you know that dx dt is nothing but velocity v, right, that is how you relate it. But if you just look at it as a second order differential equation and not the velocity v, just a new variable v, right, because here our focus is in general to learn how to handle second order and higher order differential equations. So, just imagine that dx dt equal to v, you can give some physical meaning to v, or you can just say it is some new variable, the first order derivative you call it a new variable v, and then d2x dt2, which is the equation of interest, the second order differential equation of interest, then you can write that as dv dt equal to minus k by m x. So, this is the first. So, these two equations are two first order differential equations, right, and from what you learned in last class, you can solve each of them in tandem, and so basically you will have v as a function of t. So, how does v, the first derivative, evolve as a function of time? Moreover, you will have x as a function of time. So, when you were solving this second order differential equation, your aim was when you solve it to get x as a function of time, x as a function of t, if you do not want to ascribe physical meaning to the quantities x and t. So, suppose x is some general variable, right. So, what have you done? By just redefining variables, a second order differential equation has been written as two first order differential equations, and even if you had a third order differential equation or a fourth order differential equation, by a similar redefinition you can convert a fourth order differential equation to four first order differential equation, right. If you had a fourth order, then you will say okay, dv dt equals to such and such, and then you can define even higher order derivatives in terms of new variables, and then you can solve it. So, what I shall do is basically discuss the algo. This is just our one small step more complicated than the previous equation. Previously, you were solving just one equation. Now, we are going to solve two equations, two first order equations in tandem. Now, since you have a second order differential equation, as you would be knowing from your mathematical physics course, that you would need two initial conditions to solve it, right. At the moment, we are discussing differential equation where the initial condition is given. So, you shall need an initial condition for x. So, suppose at time t equal to 0, that is the beginning of the interval, at time t equal to 0, x equal to 0 and v 0 equal to 0.1. Okay. So, if you want to give physical meaning to it, just say that there is a spring at time t equal to 0, it is sitting at the origin. So, there is no compression or extension of the spring, if you like, that is x equal to 0, and then it has an initial velocity of 0.1, right. And for simplicity, you can choose k equal to 1, m equal to 1. Of course, you can choose different values of k and m as well, and that will basically change the amplitude of the oscillation. It will change the time period of the oscillation given the initial conditions, right. Moreover, since you are solving the differential equation numerically, you have to give the interval of integration. You are going to integrate, say, you are going to look at the motion or look at the solution to the differential equation from time t equal to 0 to say time t equal to 20, just as an example. And what else do you need to be able to solve it? What is your integration constant? What is not the integration constant, but what is the interval of integration? What is the value of h? So, we are going to calculate x at different time points, and what is the difference between these two different time points, and here you can just say h equal to 0.02, and then you have to do your Runge-Kutta iterations. Suppose you use Runge-Kutta to solve the differential equation. You are free to use Euler also, but then on Euler you will have more errors, as you know, and we will discuss that and see the examples later. But suppose what is more typical is Runge-Kutta is the method of choice, right, and then you have to iterate to calculate x and v at different time intervals. If your t equal to 20 and h equal to 0.02, then the number of iterations which I shall typically refer as n iter, n for number, iter for iterations, will be 20 by 0.02 equal to 1000 iterative steps. So, what would be the algo be? It can't be very different from what it was last time. Here the initial conditions, initial values are given for the two differential equations, x equal to 0 or v equal to and v 0 equal to 0.1. Those are the initial conditions. So, the algo will be basically do I equal to 1 to niter, number of iterations, and at the end there is the endo loop, right. And what do we have to do? We have to, and for a first order differential equation, if you are using Runge-Kutta, you had to calculate f 0, right, and f 0 in our case from this equation, use this equation, and we know f 0 equal to v 0, right. That is what dx dt equal to v. So, that is what it is. So, in this case f 0 equal to v 0, then you take small predictor step, you try to evolve the system, but of course, store that in a temporary variable, because you want to calculate the slope of Runge-Kutta at different points and then average it over, as if you remember. So, x temp 1 is x 0, right. You have the value of x 0 here, and the temporary value of x 1 when the position is moved ahead for a time h by 2 is nothing by but x 0 plus f 0 h by 2. You have calculated f 0 here from this equation. But now you have another first order differential equation, and that has to be solved in tandem. So, rather than just f 0, you shall also have f 0 v corresponding to this equation, right. So, you have f 0 v, which is nothing but minus k by m x 0, right. X 0 happens to be 0, but it could also be any finite value, right. It is basically x at time t equal to 0, and then you evolve v for time h by 2. So, v temp 1 equal to v 0 plus f 0 v into h by 2. Having got that, you can calculate f 1, which is basically the values of f 0 and f 0 v using this value and this value. So, you can calculate f 1 and f 1 v. With that, you can calculate x temp 2, right, and similarly v temp 2, then, and that is also over a interval of just h by 2. Using that, this position and this value of v, you can calculate f 2 v, f 2 and f 2 v. Using that, you can calculate x temp 3 and v temp 3. Those are again temporary values of the variables, right, using which we again calculate f 3 and f 3 v. This was discussed in great detail in the last class. If you have any confusion, please refer to the end of the last class. And once you have f 0, f 1, f 2 and f 3, and similarly f 0 v, f 1 v, f 2 v and f 3 v, then we can do the actual update of the position or the variable x, and similar, which is nothing but x 0, the previous value x 0 plus h by 6, f 0 plus 2 f 1 plus 2 f 2 plus f 3. And similarly, the new value of v 0, this is not now the this is not this v 0 is not anymore the initial velocity, is just updating the new value of the velocity after time h using Runge-Kutta is nothing but the previous value of v 0 plus h by 6 and this formula, right, very similar to this. So, what have you obtained? You have obtained both the updated position and the updated velocity at time t equal to 0 plus h, right. Now, using these values of x 0 and v 0, which are calculated at time t 0 plus h, you can do exactly the same thing and calculate the position and velocity at time t equal to 0 plus 2 h, and so on so forth up till the end of the interval. After you have done this step one iteration, you can basically write down the time of integration h into d float I shall run from 1 to 1000, and write down the position and velocity at each of these times. And once you have written this, once the program has finished running, you can use these quantities and plot them to plot x versus t and v versus t, right, and you know how it is going to be. It is going to be basically sine and cos curves, because you know the solution to this differential equation. It is a periodic motion, it is a spring after all. Moreover, what can you calculate and use it as a test to validate whether your simulation is working correctly or not? You know, for a spring there are some conserved quantity, and in this case it is the energy, right. So, while you are solving the differential equation, you are also taking the help of physics, your background knowledge of physics, to devise tests to assure yourself whether you have done your calculation correctly or not, right. And for the simple harmonic motion, you know that there is a constant of motion called the energy, half mv square kinetic energy plus half kx square the kinetic energy, sorry, the potential energy, right. And so you can just plot the total energy as a function of time, if you like, write the energy here and plot energy as a function of time, and if you are doing your simulations correctly, it should be conserved, right. So, now let us see that. So, this is the algorithm for Runge-Kutta, and of course, you can do the same thing using the Euler method and the modified Euler method and the improved Euler method and so on and so forth. So, what we will discuss in a practical example, I shall show you what is the kind of solution that you get if you use the Euler method and how would the errors creep in, and then do the same, show you the data for Runge-Kutta, and what you should do is basically implement it on your own. So, that you are sure that you are able to solve a simple at least second order differential equation with full confidence, and once you have done that, of course, we shall go to slightly more complex problems. We will make this x, suppose, a nonlinear function. But let us first look at the solution to this differential equations. Okay. So, what I have plotted here is x as a function of time, velocity as a function of time, and energy as a function of time. So, this is what is there on the x axis, and the legend explains what these different colored graphs are, and on the x axis you have basically time. So, y has all these quantities, right, and this is been solved using a simple Euler method with velocity equal to initial velocity equal to 0.1, just as discussed in the notes, right. Now, this black curve is the Euler method with dt, the integration constant, or h if you like, is 0.001, right. And what do you see? So, if its position was 0 at time t equal to 0, position is 0 here, and is this black curve. Where did the blue one go? Okay. And you see that basically the position increases and then decreases and increases in an oscillatory motion, okay, hardly surprising. And what does the velocity do? The velocity is the red curve, and in case you can't see it, I will just make it thicker. Velocity was 0.1 at time t equal to 0, it is 0.1, and as the basically the position changes, it goes away from the equilibrium position, the velocity slowly becomes 0, and then it becomes negative, and so on and so forth. So, these are the two, position and velocity as a function of time. They are of course out of phase with each other, and you can see if you that the period of oscillation when k was equal to 1 and m equals equal to 1. So, that k by m is 1 essentially, the time period is 2 pi, right. So, you can just check for yourself that this position is approximately equal to 6.28 as it is expected. Now, I have done this integration with 0.001. Here I have also plotted the energy in this green line, and we will discuss energy in further detail. Now, just for comparison, I have also done the Euler integration with h or dt equal to 0.02, which is much higher, right. And what do you see? Of course, the initial part of x versus t and v versus t are exactly same as what was obtained when when the dt was 0.001, but at longer times, say here, you see that the x with dt equal to 0.02 is this blue curve, and you see deviations. Okay. You see deviations from what was plotted when dt was 0.001. Similarly, when when h equal to 0.02, the velocity, it again shows deviations. Which one is correct? Well, at least you know that the velocity should be, I mean the peak of the velocity should be constant, the energy should be constant, the total energy should be constant, and you see that when you had used h equal to 0.001 or dt equal to 0.001, the peak of the velocity always remained 0.1, oscillatory motion, kinetic energy to potential energy to kinetic energy. But when you are using a higher value of h, you are getting an error, the initial this peak of the velocity is growing higher. So, obviously the integration is not being performed in a good enough way, though it is difficult to see, but at longer times. So, at initial times they fall on top of each other, but at longer times just 3 or 4 oscillations and you see deviations, and the integration is not being done accurately for higher values of h. But that is not surprising, as we discussed in the last class that in Euler method the error, right, the local error, the error at each integration step goes as h square, and over the entire interval it goes as h, it increases the linearly with h, and that is exactly what you are seeing. So, hardly surprising. What about the value of energy? So, here I am just blowing up the value of energy, right, and you know what should be the value of energy at time t equal to 0, the position was 0 and it had initial velocity. So, the total energy was essentially kinetic energy, half mv square, v being 0.1, 0.1 square 0.01, and half of that is 0.005, and that is exactly what you see at time t equal to 0, right. Now, energies should remain constant as position and velocity exchange in their amplitude, kinetic energy to potential energy, and you can see that energy with time dt equal to 0.001 remains nearly constant. Well, nearly constant, even this has shifted a bit, right. Here you can see ideally it should be exactly here 0.005. On the other hand, dt equal to 0.02, there is a clear and distinct increase in the energy, consistent with what you saw that x was gradually increasing, or that the peak position of x was gradually increasing. So, of course, again I am emphasizing that Euler is not a great method. It works, but you have to use very small integration intervals, right. The value of h has to be 0. Now, if we did the same, now suppose we did exactly the same calculation with Runge-Kutta, right, with h equal to 0.02. It is a much higher interval, you have to take only 1000 iterations. On the other hand, if you had 0.001 to run for time equal to 20, right, the number of iterations you would need is 20 by 0.001, that is 20,000. So, 20,000 iterations when you have dt equal to 0.001 for a time range of 20. On the other hand, just 1000 iterations when you have dt equal to 0.02, and let us see how the Runge-Kutta does. So, here what I have done is plotted basically x versus time, v versus time, and energy versus time exactly as previously. No difference with v 0 equal to 0.1 and x 0 equal to 0 and h equal to 0.02. The x axis is labeled time, right. Whenever you show graphs, please do label the axis. Okay. You cannot have a graph where the axes are not labeled. So, the viewer does not even know what is being plotted, right, and energy is plotted in the black line, x versus t and v versus t in red and green lines respectively. What do you see? Well, you can see that especially if you blow up the energy with even this larger value of h equal to 0.02 over the range, the energy is perfectly within the range that we are looking at compared to Euler constant, right. So, it is much more accurate, hardly surprising because Runge-Kutta is supposed to be much more accurate than the Euler scheme, right. At each step, integration step, you are making a error of h4 and the global error in the entire range will be h cube, right. So, you will see that it is not exactly constant, only at 0.02 to the power 3. So, basically 10 to the power minus 6. So, if you blow up this energy data to 10 to the power minus 6, then you will be seeing that well the energy is not perfectly conserved, because it is the error in the energy will be only at that scale, right. But within the scale that we are looking at, it is perfectly conserved. You can go to smaller and smaller values and you see it is perfectly conserved. What happens if you change kappa? Say, suppose you changed kappa equal to 0.1. What do you expect? You already expect, you know, that the spring constant, that the time period of oscillation is going to change. This blue line is just been tried out with kappa equal to 0.1, and you can see that basically the time of oscillation will be significantly more, right. So, that is all that we have done. So, what is the message? The basic message is the Runge-Kutta is working pretty well. We have demonstrated it. You are solving a second order differential equation. You can fit your sin omega t with where you can calculate omega cos omega t and see that it matches, and that you are getting a good result with your Runge-Kutta. Okay. So, having got, you have to implement this, and after that, having got confidence in this, let us look at a slightly more complicated problem.